Welcome back. Let's talk about exponential decay. Okay, an exponential decay function is going to have the same form, y equals a times b to the x. A has to be greater than 0. The difference is that b is going to be between 0 and 1. So it's going to be something like 1/2 or 7/8, something like that. And so in this case, b is considered the decay factor. All right, so these look different. The function y equals b to the x, where b is between 0 and 1, is the parent function for the family of exponential decay functions with base b. The general shape of the graph of y equals b to the x is shown below. And so it drops off quickly and then slows down how much it's decreasing, and it still approaches the x-axis from above. So the x-axis, the line y equals 0, is still our asymptote, our horizontal asymptote to be particular. The graph falls from left to right, passing through the points 0, 1, and 1b. So again, plugging in x equals 0, x equals 1, I think x equals -1 are all critical. The domain of y equals b to the x is all real numbers. We've got arrows on either end, and we don't skip any values in the middle. Okay. The range is y greater than 0. Okay, because we start off right here, right above the line y equals 0, and our y values go higher and higher. Okay, we're going to graph y equals b to the x for 0 less than b less than x, and so we're going to look at y equals 1/2 to the x power. So again, let's make a little table of values because this is our first decay function to really look at in particular. So let's plug in x equals -3, -2, -1, 0, 1, and 2, and see what y values we get. So we get, when we plug in -3, okay, so we've got 1/2 to the -3 power, means use the reciprocal, so that's going to give us 2 to the third, which is 8. 1/2 to the -2 power is going to be the reciprocal squared, so that gives us 4. 1/2 to the -1 power just means use the reciprocal of 1/2, and so we get 2. 1/2 to the 0 power is 1. 1/2 to the first power is 1/2, and 1/2 squared is 1/4. So now we're going to plot the points, and then we're going to draw in a smooth curve. Okay, remember, exponential decay, it's going to fall as we go from left to right. Okay. Now, I like to think of this as falling from left to right. The authors like to think of this as rising from right to left. Those are analogous concepts, so whichever way you want to think about it is fine by me. Okay, so let's go ahead and do our translations. Let's look at y equals a times b to the x minus h plus k. This time, the only difference from what we looked at in video 1 is that we do have a b value between 0 and 1. All right, so we're going to graph y equals 3 times 1/2 to the x plus 1 minus 2, and we're going to state the domain and range. All right, just like before, you're going to look at the function without translations first, and then we'll consider what the translations are and get our final answer. Okay, so we're going to begin by sketching the graph of y equals 3 times 1/2 to the x, which passes through. If we plug in 0, 1/2 to the 0 is 1 times 3 is 3, so it passes through 0, 3, and 1 3/2. Well, how did they get that? They plugged in 1 for x. 1/2 to the first is 1/2 times 3 is 3/2, so 1 3/2. I like to plug in -1 also. Well, 1/2 to the -1 means use the reciprocal of 1/2, so 2. And 3 times 2 is 6. So -1, 6 is on our original just kind of guideline function there, a function before translations. Now again, if you don't have two different colors of pens or map colors or something with you, you can draw this in as a dashed curve because we're just using it to help us out. Now to get our translated graph, consider that this is x minus h, so h is -1, so we're going to go left 1 unit. It's plus k, so k is -2, so we're going to go down 2 units. So we take each point and literally just translate it, slide it over. 1 unit to the left, 2 units down. Go to the next one, 1 unit left, 2 units down, and then we draw in our final function. Make sure you label each one correctly so that I know that you know which one is your final answer. Okay, so let's talk about our domain and range. They're going to state it on the next page, but let's do it while we can see the graph. Again, no restriction on x at all, so our domain is all real numbers. Now, before we translate it, our range was y greater than 0. We've dropped down 2 units, so this is going to be y greater than -2. Okay. The graph's asymptote didn't ask for that. It's still the line y equals -2. And that's related to the fact that the range is y greater than -2. Okay, exponential decay models. When a real-life quantity decreased by a fixed % each year or other time period, the amount of y of the quantity after t years can be modeled by the equation y equals a times 1 minus r to the t power, where a is the initial amount and, that should be and, r is the % decrease expressed as a decimal. Note, let me fix these. Note that the quantity right, the individual and r. Okay, there we go. Sorry about that, guys. Okay, and note that 1 minus r is the decay factor. Okay, that's our b value. That's going to be between, this 0 is going to be less than 1 minus r, less than 1. Okay, so we're going to solve a multi-step problem. A new snowmobile costs $4,200. The value of the snowmobile decreases by 10% each year. Write an exponential decay model giving the snowmobile's value y in dollars after t years. Estimate the value after 3 years. Okay, so first we want the model. So the initial amount is $4,200 and the percent decrease is 0.10. So when we plug those in, we get 4,200 times 1 minus 0.1 to the t power. So we can simplify that a little bit to get y equals 4,200 times 0.9 to the t power. That is our model. Okay, that's the model itself. Now, to do our value when t is 3, after 3 years, you just plug in 3 for t, and you get $3,061.80. So that is it, guys. I will see y'all next time, and we will do the practice problems, and y'all will have this down in no time flat. See you in class.